Good morning. This is the video to go over questions 17, 18, and 21 in section 2.7, which is related rates. And as promised, at the end of this, there's one more assignment with, I think, 4 or 5 more, at which point we will call section 2.7 done. So here we go. 17 says, at a sand gravel plant, sand is falling off a conveyor belt and onto a conical pile at a rate of 10 cubic feet per minute. So I've got it's making a cone. It's falling off a conveyor belt, making a cone. That's the radius of the cone. That's the height of the cone. And if sand is falling off at a rate of 10 cubic feet per minute, that's a 3-dimensional quantity or label there. So that's the rate of change of the volume. That's how fast the volume is changing. So it tells us that. Then it tells us a seemingly random piece of information. The diameter of the base of, that should say cone, not the cane. The diameter of the base of the cone is approximately 3 times the altitude. Diameter is 3 times the altitude, which is the height. We'll figure out in a moment what to do with that. And then it says, at what rate is the height of the pile changing? So it's saying find how fast the height is changing. That's dH dt. And it's to find it when the pile is 15 feet high. So when h equals 15. So there is our information, and the problem in the book, I believe, did give you the formula for the volume of a cone. Probably worth knowing. The volume is 1/3 pi r squared h. Now, that normally would be the equation we would want to take the derivative of with respect to time, and we could do that. If I did that, there would be a dv dt at the beginning, clearly, and then I have an r and an h in there. So there would be a dr dt somewhere and a dh dt. In particular, that dr dt would worry me a little bit. The problem is asking for dv dt, and the problem told us dh dt, but that dr dt we wouldn't know what to do with, which is where this comes into play. Let's use that and see if we can't get rid of a variable here. So the diameter of the base is clearly the 2 radius. So I can write this as 2r equals 3h. I'm just going to solve that for r. I get r equals 3 halves h. So what turns out I can do here is this r equals 3 halves h. I can substitute in for that. I've not yet taken the derivative. But this way, all I will have is v's and h's. So I have v equals 1/3 pi, instead of r we said was 3 has h squared h. By making that substitution, now I'll clean this up in a little bit before I take the derivative. But now my derivative will only have dv dt, which is the one I'm trying to find, and dh dt, which the problem gave me, or no, I said that backwards. dv dt they gave us. dh dt is what we're trying to solve for. So now let's just clean this up just a little bit. This is 1/3 times pi times, what's that, 9/4. And then h squared times h is h cubed. And at this point, I might combine the 1/3 and the 9/4. That's 9/12, which reduces, I think it's 3/4. 3/4 pi h cubed. There's an equation for the volume of that cone. Now I can take the derivative of that with respect to time. So that would be dv dt. And the derivative of 3/4 pi h cubed, with the 3 out front, I get 9/4 pi h squared dh dt. And now I think I can substitute known values in for everything. dv dt, it told us, was 10. 9/4 pi. It said to find it when h is 15 squared, and then the h dt is what we're looking for. All right, 15 squared is 225. Tell you what, I might do a couple things here. I just got to be careful cleaning this up. I might multiply both sides by 4 to get rid of that 9/4. That becomes 40. Now I have 9 times pi times 225 times the HDT. 9 times 225, you get a calculator, that's the 1800 plus 180, 1980, 2025, I believe. And then you're dividing both sides by that. You get 40 over 2025 pi, and pay attention, the pi is in the denominator, make sure that's clear. Which turns out to reduce, divide both by 5, and I'll do this up here. Turns out to be 8 over 405 pi. And that is the rate of change of height, which is just feet per minute. So I will tell you, it's a pretty common context to have something in a cone, a conical pile. And I will note that this information that they gave us that we weren't sure what to do with, like they're going to have to give you some sort of information about the dimensions of the cone, or else we won't be able to finish. So I think number 18 also has something. We're going to have to figure out something similar. So that was 17. 18, a conical tank, vertex down. That looks like this. 10 feet across the top, 12 feet deep. So there's that cone. Water's flowing, that's a 10 at the top there. Water is flowing into the tank at a rate of 10 cubic feet per minute. So that is still the rate of change of the volume. I think it's the same rate as last time. Find the rate of change of the depth of the water. I'm still going to call in this cone. Now, this is going to confuse me a little bit here. I'm going to just draw some random water level here. And I'm going to call this distance R, and then this distance H. So I still have a radius and a height as the water is filling. Find the rate of change of the depth. So I'm trying to find the H dt when the water is 8 feet deep. So when H equals 8. And again, I have the same equation for the volume of a cone. V equals 1/3 pi r squared H. But again, I have R's and H's, and that's more variables than I wish I had. So I have to figure out, remember in the last problem, I had that equation, D equals 3H, from which I was able to get rid of the R. Turns out we can do that here. The fact that they gave us the dimensions of the cone, I can actually draw a couple similar triangles here. The little one is my R and my H. That's the water. The big one is 12, and if it's 10 up all the way across the top, it's just 5, half of that. I have two similar triangles because there's a right angles there. So I can write that as a proportion. I can write this as 5 over 12 equals R over H. I think I want to solve this for R. So again, I still want to, just like in the last problem, I want to replace that R with something in terms of H so that my equation only has V and H in it. So if I cross multiply this, I get 12 R equals 5H. And I divide R equals 5/12 H. So I am going to substitute this in for that. So I will write this right here. We'll change to purple. I have V equals 1/3 pi. Instead of R squared, it is now 5/12 H squared times H. All right, now I can clean that up a little bit before taking the derivative. So let me go like that and like this. There we go. So this becomes V equals 1/3 pi. Well, 5/12 times itself is 25 over 144. And I'm going to have an H to the third because I have H squared times an H. Now I might clean up the 1/3 of the 25 1/44. I'll put it down here. V turns out to be not 1/3. I was going to clean that up. 1/3 times 25 44 is in fact 25 out of 432, I believe, pi h cubed. Make sure that matches. It does. Notice now that pi is not in the denominator, and there went my lights, as opposed to our final answers where it might be. So just be careful where you write that. I think now I'm ready to take the derivative of that equation with respect to time. So that becomes dv dt on this side. I move the 3 out front. 3 times 25 for 30 seconds is 75 for 30 seconds, and it's pi h squared dh dt. Now I'm going to plug in some numbers. And also, let's do some reducing. It turns out that 75 for 30 seconds, I can reduce that. Both of those divide by 3, so I might write that as actually 25 over 144. That's just that fraction reduced. Pi h squared dh dt is what I'm trying to find, and dv dt was 10. All right. Oh, and I should have put a number in for h. Sorry. It said when h was 8. That shouldn't say h squared. It should say 8 squared. All right. Now, again, I'm going to do the same thing in the last problem. I'm going to multiply by 144. That makes 1440 equals, let's also do 25 times 64, which I believe is 1600. 1600 pi dh dt, and I just divide. Dh dt equals 1440 over 1600 pi. And here the pi is absolutely in the denominator. That fraction, it turns out, reduces to, I did it earlier, oh, it's 9 over 10. Turns out to be dh dt, turns out to be 9 over 10 pi, and it is feet per minute. So 2 examples where you're dealing with a cone and the volume of a cone. Again, pretty standard, pretty common context. All right, last problem is 21, and really there are a part A, B, and C, and each one of those is a different equation, so it's kind of 3 problems. And actually part A here has 3 different numbers to plug in. So a little deceiving when I say one problem. And it says a ladder 25 feet long is leaning against, I can spell the word against, despite what it says here, is leaning against the wall of a house. The base of the ladder is pulled away from the wall. The base of the ladder pulled away from the wall at a rate of 2 feet per second. So since I labeled this x, I would argue that this problem tells me that dx dt being pulled away from the wall, so it's increasing, equals 2. And part A wants me to find how fast the top of the ladder is moving. So find dy dt. And then it gives us 3 different times. We have 3 different numbers to plug in at the end. So I need an equation that relates to 3 sides of a right triangle, which hopefully you recognize is the Pythagorean theorem. So I have x squared plus y squared equals 25 squared. Let me say what I said yesterday. A common question at this point is, you put 25 squared, why didn't we put in 7 for x? Or why for 25 squared didn't we use another variable? They got to be real clear on when should you use a variable and when should you use a number. And my answer is the same as it was yesterday. If the quantity changes throughout the problem, it's got to be a variable. And as this ladder gets pulled away from the wall, x and y both change as that ladder slides. But the length of the ladder, which is 25, does not change as that ladder gets pulled away from the wall. So that's why that 25 squared is not a variable. All right, now let's take the derivative of that with respect to time. The derivative of x squared is 2x dx dt. Similarly, the derivative of y squared is 2y dy dt, and that equals the derivative of a number which is just 0. And now I'm going to start plugging things in. So I have 2, and again, the first one said when x was 7, 2 times 7 times dx dt, which the problem said was 2, plus 2 times y, which it looks like I don't know, which we'll come back to in a moment, times dy dt, which is what we're trying to solve for, equals 0. I don't have a y value. So we saw one of these yesterday. At the moment when x is 7, so that's 25 because it's always 25. When that happens to be 7, the question is, what does y equal? So we need to do 7 squared plus y squared, equals 25 squared. That turns out to be Pythagorean triple. Y turns out to be 24. You maybe should recognize 7, 24, 25 as a Pythagorean triple. Might be worth recognizing. So that turns out to be 24. And now we just finished solving this for dy dt. So that's, what's it, 28 plus 48 dy dt equals 0. So 48 dy dt, if I subtract, is negative 28. And I get dy dt is negative 28 over 48, which reduces to negative 7/12, I believe. Negative 7/12, and that is feet per second. Should make sense that that quantity is negative because as the ladder is getting pulled away from the wall, the height y is in fact getting smaller. So there is the answer at 7. Now I'm going to be a little lazy and let you do the other ones. To do the rest of part A, you're just plugging in different numbers for x and y. So I've got it turns out that the answer for the second one is 3/2. That's when x is 20. I'm sorry, when x is 15. And the last one turns out to be 48/7. Oh, they're negative, sorry. And negative 48/7. So you can go back and do the other parts of part A. There's the other answers. Those two are the solutions to those two. In the interest of time, I won't do this. But it's the exact same equation, same process. All right. Part B, same ladder. Now it says, consider the triangle formed by the side of the house, the ladder, and the ground. Find the rate at which the area of the triangle is changing. It still tells us that dx dt equals 2, but it wants to know dA dt, the rate of change of the area. And it says when x equals 7, when the ladder is 7 feet from the wall. So I need a formula somehow relating the area of a triangle. That's just 1/2 times base times height. So the area is 1/2 times x times y. Notice I don't need the 25. If I give you a right triangle and I want to find the area, it's just 1/2 times base times height. The length of the hypotenuse is not part of that formula. All right, so let's take the derivative of that with respect to time. So we'll start over here, dA dt. I have to product rule this. Gotta be careful with the 1/2. I'll attach the 1/2 to the x and product rule it that way. I could have left the 1/2 out front, opened up a parentheses, and then product ruled it, and then distributed the 1/2. Would have been the same result. So I'm going to use the product rule. Product rule is the first times the derivative of the second. And the derivative of y is dy dt plus the second, which is y, times the derivative of the first. And the derivative of 1/2 x is 1/2 dx dt. All right. So now can I plug things in? dA dt is what I'm looking for. 1/2. It said when x was 7 times dy dt. Well, fortunately, in part A, when x was 7, we found dy dt. It was negative 7/12. Turns out we need that conclusion for this particular problem. So that's negative 7/12. And then plus, again, we need we need y. We did it earlier. When x was 7, y was 24. And then times 1/2, and dx dt is 2. The problem gave us that. And now it's just carefully evaluating this. So dA dt, that's negative 49 over 24 plus, my 2's cancel, 24. Now I could decimalize that. Turns out that if I write that as, if I common denominator it would be, what's that, 576, I think, over 24. I just multiplied this by 24 over 24. So that turns out to be 527 over 24. This is dA dt, that would be feet squared per second. So there's the rate of change of the area when x is 7. The last problem is part C. It says find the rate at which the angle, which I've labeled theta in this drawing, which the angle theta between the ladder and the wall is changing. So ladder's falling away, the angle appears to be getting bigger. Also, how fast it's getting bigger. So it still told me that dx dt was 2. Okay. I need an equation. It's got to have theta in it. So it's going to have to be a trig equation. So let's think about this. I really have some options here. I'm going to write out all 3 options, and we'll figure out which one makes the most sense. I could do the sine of theta equals, now I've got to be careful. Sine is opposite over hypotenuse. And given this triangle, given where theta is, that would be x over 25. Or I could use the cosine of theta. Cosine is adjacent over hypotenuse. And for this triangle where the theta is, the adjacent is y, the hypotenuse is 25. Or I can use the tangent of theta. Tangent is opposite over hypotenuse, which in this drawing would be x over y. I can use any of those. And if I did those, they'd all have a d theta dt. The first one would have a dx dt. The second one would have a dy dt. The third one, tangent, would have both a dx dt and a dy dt. Any of them would work, but since the problem gave me dx dt, I'm going to choose this one, which is only going to have a d theta dt and a dx dt. So you wouldn't have to pick sine, but I'm going to pick sine. All right. So we're going to take the derivative of this. I'm going to rewrite this for a second. The sine of theta equals 1/25 x. That's really what that says. Now I'm taking the derivative of this with respect to time. So the derivative of the sine of theta is the cosine of theta and then d theta dt. There's that d theta dt. Equals the derivative of 1/25 x. Well, the derivative of a number times x is just a number. So that's 1/25, but then I still need the dx dt. Okay, now I need to substitute some stuff in here. Dx dt is 2. D theta dt I'm trying to find. So I go up here. I need the cosine of theta. So I'm going to leave I need the cosine of theta, which I'll come back to in a minute, times d theta dt, which is what this problem is asking for, equals 1/25 times dx dt, which is 2. As far as d theta dt, at the moment when x is 7, so again, if I put a 7 here, I need the cosine of, it was cosine, right? I need the cosine of theta, which would be adjacent over hypotenuse, which is this over that. Well, what is y? We did it earlier. When x was 7, we used the tag there, y was 24. So at the moment when x is 7, that's 24, which makes the cosine 24 over 25. And now I can multiply both sides by 25 over 2, and I get nope, that's a lie. Hold on, fine. I said the wrong fraction, then the lights went out. I'm going to multiply both sides by 25 over 24, since I'm solving for d theta dt. This becomes 2 over 25 times 25 over 24, which reduces to 1/12, and that is radians per second per second. So there is that example. All right, and I am done, and your last assignment in 2-7 is on page 196, and it is numbers 26 through 30. And again, I will put a video eventually with the solution to these, and then we should be good to go. So I think that's it. Have a great Thursday. If I can figure out how to get this thing back up here and stop. There we go. All right, see ya.